All right. I think we're live. Thank you, everyone, for joining us in this live webinar. Today, we're going to talk about recommendation system, RecSys, and it's going to be a gentle introduction on how they work, how they operate, and how you can actually make your own. I am Lex. I'm the head of strategy at HubSpot, and I'm joined by David Jalaba, our head of data science. And what we'll do is I'll do a very short intro about who we are. Then we're gonna go from the top level, essentially explaining why those recommenders are so great, uh, how they work, maybe a little bit of an overview of some of the systems in the industry, and then we'll start to go down in more of the technical layers, how the ranking works, how the architecture works, and then finally, after showing how yeah, HubSpot may help with that. A short demo and an actual implementation of those systems. All right. So about us, we are an AI lakehouse. We pioneered the feature store category sometime in 2018, 2019, and we essentially increased our capabilities over time to be a full-fledged MLOps platform on lakehouse table. So that's the AI lakehouse. We have a few presentations lined up on all of those levels of abstractions in the data platform and so on. I invite you to check our event page or just email me if you want to ask how we operate. We do have a free platform, also really great to just try and just go around. There is no time bound or there is no time limit, so you can practically deploy your own AI system in the cloud for free. There were just some limitation in terms of storage and so on, but feel free to go. And obviously, we are in production and in many of our customers' environment, and this is where we see those systems being implemented. So it's also a bit of the insight we gathered along the way in actually putting those things in the world. I'm not gonna go too far into the self description of things. We are an extremely high performance platform. We've been benchmarked and peer reviewed on those performances. So one of the things we are extremely proud of at Hotbox is our ability to provide fresh data to the model. So the moment an action happens, and to the moment your model needs to react to that action is extremely short. And we are, in fact, the fastest in the world in this sort of capabilities. We have some other benchmark. I invite you to go to our repository and you can actually just benchmark us. Two aspects that I really like to present, like you work in an ecosystem of data that already exists. But unfortunately, and this was a recent study by a very big vendor and the economist at the end of last year, most of the architecture on that data actually do not support the AI workload of today. And that's not necessarily only Gen AI, that's Gen AI plus everything else. And the other aspect is that the benefits of AI are really, really, really evident when you're talking about hyper personalization. So, real time recommendation, individualized content, dynamic content, all of that depends on the ability of your infrastructure to know what happens in real time. And especially for real time recommendation systems, that creates a real dynamic environment of products. So, you can deploy us everywhere. No need to dwell on that. And we do have obviously quite a range of use cases and customer. We will have actual dedicated industry webinars are coming, especially for e-commerce, retail, and different contractors. So I invite you to check our page for that as well. Now, why are recommendation systems so addictive? It's really on the way, the thing that they are designed to produce. And they are designed to produce two main things, one of which is increase the satisfaction. So they are designed to increase the user's satisfaction towards what they're seeing, what they're consuming. And in addition to that, they are designed to increase retention. And sort of in the architecture of those technologies, it's really both. Because you increase the satisfaction, you will increase the retention. And because you increase the retention, perhaps it's a function of the satisfaction of the product. But those are the real two aspects that are recommended does. And therefore, they are extremely addictive. Uh, and because they are addictive, and this is a word that carries a little bit of weight in itself, they are indeed risky. They can create certain, addiction to what platform and consumption patterns and so on. I will not go into the whole risk assessment of recommender system, but I can mention like one of the most prominent sort of aspect of it, which is the filter bubble. And the very, very simple way to see a filter bubble is like if you are, let's say, a Nike consumer and you start to browse on the platform and start to see a lot of Nike products, eventually you might end up in a filter bubble where all the products you see are within the realm of that brand, and you will maybe lose visibility on other brands. A lot of companies have mechanics to sort of prevent that, but it's still very hard to prevent to be in a bubble, because maybe I will still show you some that thing, but you'll end up in a software bubble. So this sort of bubble and tunneling effect in social media and e-commerce is quite common. And a lot of strategies are in place at different stages of the model and the architecture to essentially overcome that. But on the high level, you want to recommend to people what they like. So two of the most successful products in the world, and they are AI powered, are TikTok and Netflix. And the reason they are so great, and especially for TikTok, is directly linked to the ability to show to the users in extremely fast what they really want to see. On the high level, it looks like something like this. We will actually go into the detail of this sort of architecture. It's actually exactly the architecture we'll show you a bit later with more detail, more refinement. But it's a loop, right? It's a loop of interaction of nonverbal action, and all the, let's say, all the things you do on the platform are correlated to your interest towards a certain content. So TikTok works especially well because the format is short. So your like, your swipes, the fact that you share, maybe the fact that you bookmark, all of those interactions are gathered about the users, and then they will create a whole ecosystem of potential videos to show back to the users. So you can see how this bubbling effect can also take place. Uh, Architecturally, I will not go into the depth of this specific architecture, but one thing that I should mention, like this is a real-time system. So it has a very, very efficient way to process the data, typically with Flink and other aspects, in order to give feedback loops to the users within minutes of certain action. So a typical example is like when I start to watch pizzas or like food, French food, in my case, in TikTok, I'll end up with French food and pizza for the next week and a half on my feed. And that's fairly typical. That's a fairly, it's a feeling that everybody can sort of experience for themselves. Netflix has the same logic, so that they might have different markets, and you have to also understand that while the general flow is very, very similar, and they have those banding policies. So this is where you provide all the options that might not be exactly within the recommendation or a bit further away from the recommendation. We just like mix it up essentially. So all of the companies will have banded strategies, but the flow is always the same. Collect real-time interaction about what's the users doing on the platform, and then in regard to that, or like correlated to that, provide them recommended content. One thing is, if you really think about it, not most, but all of the popular products in the tech scene at large are actually using a recommendation system, because they all want you to consume what you like. And so the theory is that if you see more of what you like, the more likely you are to come back. So increase retention, and the more likely you are to consume, increase perhaps satisfaction. And so the recommender system is sort of the discrete technologies that empower all of the most popular tech products today. And so with this sort of like very broad overview, I'll leave it to David. So I'll just switch. I'll stop presenting. It's going to be the same slideware, but David is going to take over, and we're going to look at the architectural sort of aspect. David?
Yes,
Yeah.
right. Thank you, Lex. And I hope you see my screen now. Yes.
Yes, we see your screen.
So,
Just go ahead.
so what are the recommender systems? So basically, they are systems for filtering the information and providing to the user personalized to them based on their past experience, what articles they interacted with, what is trending right now. And in the information filtering systems, there are a couple of paradigms. One is very known is content-based filtering. Okay, so if the user interacted with certain articles, maybe we can recommend similar articles, so maybe she will be interested in it. Another paradigm is collaborative filtering. Okay, we can find a similar user in our database, and what that user interacted with, we can recommend to the current user. The kind of a drawback here is that it's a single model searches. We are not utilizing both articles and then user information in the same space to hyper personalize it and to make more robust. So then, how can we do it? It's one way is to achieve this is it's embeddings. So we have a recommender systems has a very high dimensional data. There is users will have a multiple tables or information. So it's the same as the article. So we want to compress it in space and then uh, conduct a semantic search. So word embeddings, for example, is a very good example. So you can compress high dimensional data as a text. Then you will find out that the man and king are very related, very close to each other in a space. Same with the women and queen, and all of this will be very close with each other in the embedding space. Same goes with the country, and countries and capitals will be very close related in embedding space as well. But however, again, what we miss here is it's still a single model. Now the question is, can we take both embeddings for the users and embeddings for features for the embeddings, features for the articles and the users, and the map in the same space? And then question is yes. Answer is yes. It's we can use a two-tower embeddings model. In the two-tower architecture, basically, we train user features and we take user features and item features, map is to the same space, and then depending on the loss function, we can identify if interaction will be higher or low. Now we saw the one aspect of the recommender system, so we can map this in the same space, but it's the tower embedding model is the one piece in the puzzle. So this goes to this will be in a candidate generation box here. So if we will have millions of articles, like in TikTok, you will have millions of videos, or in the fashion industry, millions of items to recommend to the particular user. So when the user enters some search or context, you want to generate a candidate. That will be hundreds. So then you want to, hundreds is still too much to recommend. So you want to decrease it by filtering and ranking. So then we will come more arbitrary number, let's say 5, that the user can see it in their screen, and then choose between the recommended items. So if we go a little bit deeper to it, it's so what will happen, it will take some data related to the user and then articles, and then you will do feature engineering, you will compute embeddings. Then these embeddings will be saved in a vector database to conduct a semantic search. After we generated the articles, you want to filter them out because they might be not relevant anymore. Maybe in that region is not available, etc. And then after filtering, you want to rank. So it's a different model. So you will develop a ranking model, for example, based on the what if a similar user was shown this article, did they interact or not, or what was the type of interaction? Did they bought it, or just looked at it and ignored it, etc. So then the ranking model will the final step. It will select the top candidates, and the user will get its recommendation. So now we cover the system itself. What is needed to construct such a complex system? Then Hopsworks is provides. You need a machine learning operations platform like Hopsworks, which can handle all this. First is complex architecture, and then also handles um, data and the latency requirements. Right. So let's go. So in the Hopsworks, in the high level, first of all, to conduct such a system, you need to perform follow the feature training and inference pipelines paradigm. We will not cover it right now here, but we have a lot of blog posts related. So you're very welcome to check our website. So you need to engineer the features and train the models, and then deploy. So use some deployment framework. In this case, I will go deep down. We use the K-serve and how to organize it to handle basically the logical flow, because we will have a couple of models deployed when the user starts to interact. So what happens is that the user will enter some search word, or maybe is searching some item. Then based on the user and then item embeddings, we will generate the candidates. Candidates then will be filtered, they're ranked, and then it will be given the chosen candidates will be recommended to the user. One of the important aspects in this system will be feature freshness. That's what Lex also mentioned. The feature freshness is once the event is generated, and the times the predictions are outputted. So, as a rule of thumb, in the recommendation systems, 2 seconds is important to end. That includes, user entering some clicks and then also generating impressions. So, if you are in the ML team, your time budget will be much lower. Let's say 200 milliseconds. So you have all these 200 milliseconds to get the event, generate the features, generate candidates, rank it, filter it, and then output the prediction to the. So then impressions will be generated. So Hopsworks comes with a very high throughput and a low latency database, so you can retrieve the features in a sub millisecond level. It also supports frameworks like Flink, which was used in the TikTok and Netflix recommender systems. So you can compute your features in the real time. But Hopsworks is an open platform in terms of you can also use the Feldera, for example, which is more SQL based real-time feature engineering framework. On top of this, especially dealing with such a complex system, you need to have some guardrails to make sure that your data is correct. For example, you can do some expectations during the feature engineering. You also need to do some monitoring when maybe features started to shift the time you train the data. So you need some kind of knowledge alert when is the time to degrade the current model and promote the new one. Plus, obviously, I can show in the demo in the next sections that you need some governance. You need to know which model is related to which feature and what's a version of that and what was activity related to them. On top of that, obviously, there is as an ML team, you have to make sure that there is a zero training to serving skew, and that it gives you a capability and the guardrails that you don't make any unintentional mistake. Right. Let me quickly show the demo. So this is the deployment already running, and here we just for demo purposes I want to show how this when the user interacts it. So it's already sending some interactions to the backend, the Hopsworks, and the new recommendations are coming back. So this is usually how the TikTok and all the systems are working. So you have the very live interaction, and then so it interacts immediately, or gives the recommendations. Platform itself, this is how it looks like. We can see here, I mentioned briefly the governance. It's as a data science ML team, it's nice to preview data. You can see statistics. You need to monitor a feature to see if there is any shift. For example, something might happen. For example, in a COVID times, the user behavior changed. So you need to detect such a things. And then of course you can monitor the metrics, your online feature store, and how many requests are coming, and what are the basically latencies outputted to the system. This is very briefly. Lex, would you mind? Would you like to
Yeah,
continue? Show them? Yeah.
yeah. So in this use case, the core idea is that you need to be able to have enough visibility end to end in order to complete and create those sort of systems. Like having a disparate set of tools, like a sort of disconnected from one another, make it really, really hard to have a very consistent system. So feature store are the de facto sort of data layer for this. And so that's what David was just showing. But you need a bit further than that. You need also versioning of the data because you need to be able to look back what happened. So whilst the provenance is important to really look at the lineage of the whole, let's say, journey of a single feature toward a specific model, you also need to be able to version all of those data sets. So in HubSpot, we do it, I was about to say quite simply, it's not quite true, but what we do is we version both the schema and the data itself. So that means that if there are breaking schema change, typically something like dropping a column, that would mean that there is a new version of this feature group for this table that will happen. And so if you have a system that depends on something extremely real time, that means that this new feature group will not alter the whole flow of the rest. And we do a few neat tricks that are also quite relevant for a real-time system. One is that we compute all the descriptive statistics of the system, and we have feature monitoring. So I don't have it activated here, but you can activate it if you try. So the general idea here is that if there is sort of a shift in the data set itself, we will know that the model will need to be retrained. And then you can, go on and on set and create your own mechanics of retraining for that. But that's a very powerful tool. And one of the reasons we are able to do that is because we keep the data untransformed. One thing that I should mention, and that's typically true for recommenders, is like a lot of the user data might not be in this sort of platform, and it's not necessarily meant to be. It might be in the data warehouse specifically. Let's imagine something like Snowflake, and in that case, you're not incentivized in order to use those recommendation architecture to move all that data into a new architecture. So you will need something that's slightly more flexible, and evidently, we provide a solution for that where you will actually mount the tables into HubSpot, so they will become external, and we can point to it. And only the latest values will be available online, so you will be able to actually retrieve it in real time. So that allows for much more flexibility, but also like not really replacing the system. Uh, Upworks as a platform as a whole is end to end. So actually those models are deployed. So the thing that David just showing is a stream API. Actually the underlying model is here, right? The two underlying models are here. And Upworks will provide the endpoint and the REST API to actually query those models. And you will have also some metrics of actual, response time, etc. So it's fairly nimble. And one of the major benefits beyond, let's say, an architectural sort of like everything box is really the lineage and the ability to have a clear view of the whole system altogether. We are using K-Serve under the hood, so, it can scale down to zero. So it's like, yeah, you can manage quite a great amount of resources and also well. Um, some other aspects, there is a model registry. Evidently, you will also have the lineage in the model registry. takes a little moment to load, but here is the same. So the view is exactly the same as the one I showed in the earlier view. It's just that this is from the model perspective, not from the feature perspective. And again, everything is versioned, so it gives you a very neat way to actually see everything and so on. One thing, and that's maybe sort of a European bias, perhaps. We do have, besides validation, we also have like governance aspects. So you can actually create your own layer of metadata on top of all those systems. And that's extremely helpful if you want to do things for governance or for, private data and so on and so forth. So I didn't create a PII tag, but I have a data governance tag. And if I apply it, then I know that this feature group, this table is actually maybe prone to, needs to be governed and so on. And you can create this sort of complex schemas and so on your own. Uh, Other benefit, I have two projects. They're isolated from one another. I'm actually only a user in this cluster, so there is probably more projects in the cluster, and therefore there are many more features from different aspects that I can actually ask. So there is this recommended course to which I don't have access. There is probably other recommended systems in place from different members of the team. And you will have this sort of ability to also create a more complex data mesh within the organization, while keeping an ability to actually retrieve the data that is needed to empower your ML systems. Uh, Upwork comes with its own development environment as well. You don't have to. In many things in Upwork are really just like, if you need an end-to-end platform, it's there for you. But if you already are happy with your, let's say, experimentation, etc., you don't have to port it to HubSpot. If you're happy with your data warehousing, you don't have to port it in HubSpot. What the platform cared for really is to provide a real-time ecosystem that is compatible with all the, let's say, the data sources and can benefit most of the like very complex use cases, such as recommendation systems. Uh, I got a bit salesy here, but it's actually true. We support Git, we support alert, so you can alert. So when the model start to degrade or decay, you can actually have Slack alerts and so on to actually alert the team that might be in charge of it. And so there is a lot of like small and discrete aspects. I think the one that is maybe more relevant, especially when you are building complex systems that might be layered on top of layer of different models and iteration, in the view. And so here, the very cool thing that we do is that we actually, maybe not in this one, that we actually separate the transformations between those that are model dependent and model independent. And so what it allows you to do is to look at those, and let me just maybe take a customer ID here. So you will be able to actually apply those transformation depending on the model. Just trying to find one where it's more obvious that it's there. It seems to me that it might not be. Let me just restart. Oops, refresh that. Actually, I might have it in my other project. I don't have a view in my other project. Great live demos. Up, maybe here. Serving key. No. Okay. Not success. Well, eventually the idea is that those transformations are applied on the data that you retrieve, not on the data itself. So the mapping of those features essentially can be different for model, but the original table is unaltered. So that really allows you a lot of experimentation, but also diversity in creating different models, different architecture, without recreating a new pipeline each time. Like trying to re-engineer the whole system. I think that's about it, really, for sort of this part.
And it's in transaction, Lex, if you want to show.
In transaction, I don't have the picture. Oh, wait, maybe did I filter?
If you go to okay.
If I go to which one you say?
Feature groups, you can do a model independent transformations.
Aha. Transaction. Yes.
And you can scroll down. Yeah,
Yeah.
then
So yeah, the transformation here is essentially applied only after the retrieval. So you can have your own transformation as well. You're not necessarily have to use ours, but it's fairly vanilla JavaScript, sorry, Python. Okay, that's about it for this part. Yeah, I think that summed it up. Thank you, everyone, and catching you next time.